Welcome back to the Deep Dive. Today, we are going deep, I mean really deep, into the physical foundation of our digital world. We're talking about the data center.
Exactly.
If you've ever sent an email, streamed a movie, maybe trained an AI model, or even just used the cloud to store your photos, you are relying completely on these anonymous, massive, windowless buildings.
Right.
So today, we're lifting the hood. We want to look at how they're actually conceived, financed, and built from the ground up.
It's this infrastructure that's somehow both completely invisible and absolutely vital. I don't think most people realize that the reliability of their favorite app, it depends on meticulously engineered concrete,
Right.
on highly specialized strategies just for removing heat, and an electrical infrastructure that, it rivals a small city in terms of its power draw and complexity. It's just immense.
That is exactly our mission for this deep dive. We've gone through source material that really focuses on that meticulous architectural planning, the engineering, the power planning, everything required to build the world's digital backbone. Our goal here is to intuitively explain why these structures, which, they often just look like huge, bland warehouses.
Yeah, with big boxes.
Why they are, and this is no exaggeration, among the most complex, high-stakes building projects on the entire planet. We really want you to walk away from this understanding the true genius and the intense pressure behind every single decision.
And that pressure is the essential context for all of this. We are witnessing an absolute explosion in demand.
It's off the charts.
It is. It's driven primarily by the need for AI infrastructure, but also, public cloud expansion, 5G services, high-res streaming, the pace of construction that's needed just to keep up. It's just staggering.
Right. It's a race. It's a race against time and against computation itself. Our sources point out the sheer scale of the investment that's driving this. Generative AI spend, just by itself, is projected to top $650 billion by 2028.
Which is an almost unbelievable number.
Just think about that figure for a second.
Yeah.
That amount of money, it translates directly into needing massive, perfect facilities. And they have to be built not just quickly, but with unwavering precision in every single phase.
It just creates this high-stakes environment where time literally is money. Success in this field. It doesn't really hinge on the construction crew being fast. It hinges entirely on sequencing every single pre-construction milestone correctly.
To all the planning stuff.
All the planning. If you miss one step, if your estimates shift, if a permit gets delayed, or, if a critical supplier slot is missed, the ripple effect can be disastrous. It can push the go-live date by quarters and incur these massive financial penalties because you missed your client's service level agreements.
So this is really a game of perfect foresight.
It absolutely is.
Okay, let's unpack this then.
Right.
Because before any physical construction starts, there's this whole universe of planning that has to happen. We need to really distinguish between development and construction. So what defines development in this high-demand world? It sounds like it's more about high-level financial and, frankly, political negotiation than it is about engineering.
You're absolutely right. Development is the entire pre-construction scope, and it involves massive financial and political alignment. It's where you secure the site, the committed power, the necessary local permits,
And money.
the precise budget, and, critically, the procurement path for systems that might take over a year to even fabricate. It sets the technical scope, it aligns the capital structure, and it locks in the risk profile for the next decade or more.
And construction is.
Construction, simply put, handles the physical build, pouring the concrete, laying pipe, installing wiring. But it's that development phase, which we can break down into 4 critical lifecycle phases and 8 specific stages, that delivers a truly build-ready site, a site that's free of fatal flaws.
So we're talking about avoiding that classic construction failure where, you start digging a foundation only to realize 6 months later that the utility commission won't approve your massive power requirement.
Exactly.
Or you hit some unforeseen zoning snag. You're building the fortress around the project before you even lay the first brick.
Precisely. Delays in these pre-construction stages, things like permit gating, utility coordination, or even environmental impact assessments, these can stall mobilization by quarters. If a hyperscale client expects to start deploying their servers on a certain date, and you're delayed by 9 months because you missed a long-led equipment slot, the penalty fees alone can bankrupt an entire project.
So you have to align scope, risk, and delivery speed, all right, at the very beginning.
You have to.
Let's dive into those early stages then, which fall under phase 1, planning. This is where we're defining the digital needs, almost like that, defining the brain of the building before the skull even exists.
And the first stage, what we'll call 1A, is IT load and demand validation. This is the absolute starting point. It's the foundation of every single decision that follows.
Okay, so what does that mean in practice?
It means you have to forecast the compute loads. Is this for AI training? Is it for general cloud infrastructure, high-density storage? You have to translate that forecast into cabinet-level power density and cooling targets.
And if you get that wrong?
If you forecast, say, 20 kilowatts per rack, when your client actually needs 50 kilowatts for their specialized AI gear, everything that follows, from the size of the generators to the structural load on the floor to the utility transformer capacity, is critically, fatally underestimated.
That seems like an enormous margin for error. And our sources say the crucial project management tip here is to coordinate utility interconnection filings and these things called load letters early to secure queue slots. Why is securing that slot so absolutely critical right now?
Because the electrical infrastructure for a major data center, and remember, we're talking hyperscale facilities that often require 20 to over 100 megawatts. It doesn't just exist waiting for you to plug in.
Right, it's not like an outlet in the wall.
Not at all. The utility company has to plan years ahead. They often have to build entirely new substations or reinforce major transmission lines just to service your demand. So when you submit your load letter, you're essentially getting in line. And it's often a queue that's already months or even years long, competing with other massive developments.
And what happens if that estimated load shifts mid-cycle? Let's say your client suddenly decides they need 30% more AI capacity than you originally planned for.
Shifting those load estimates mid-cycle can be catastrophic. The utility will, in most cases, require you to resubmit your application, which often sends you to the back of the queue. If you lose months or even a year waiting for the utility to re-engineer their infrastructure, that delays site energization by that same amount of time. And that is a direct trigger for massive project overruns and those client contract penalties we talked about.
So that estimated peak load needs to be locked down, rock solid, early.
Absolutely. When you're submitting those interconnection and load letters, they have to be validated by the utility with a stamped committed letter.
Which leads us directly into stage 1B, site selection and land control. I mean, you can't just buy cheap land out in the desert anymore, can you?
No, not really. It's a highly strategic search for a very specific set of optimal conditions. Land control, whether you're buying it, doing a long-term lease, or an option agreement, is gated by those critical utility and fiber factors we just discussed.
So power and connectivity come first.
Always. You need to confirm local zoning compatibility, planning overlays, but most importantly, you need absolute validation that power and fiber accessibility is there. It has to be either committed capacity or at-risk capacity. You need stamped letters from utilities verifying that capacity is available before you lock in any construction milestones.
So the location isn't just about cheap land. It's about mitigating these long-term risks, things like seismic activity, flooding, extreme temperatures, while also ensuring that you have optimal uptime and low latency for secure cloud delivery.
Absolutely. Think about the resilience aspect. A poor site selection can lead to higher energy costs because you have to overcompensate with cooling. It can lead to poor connectivity if your fiber backbone isn't redundant, and it exposes you to natural disasters.
A good site plan is really a 30-year plan.
It has to be. It has to be able to handle a major hurricane or an extended drought without failing. Geotechnical surveys, which check soil stability and water tables, are absolutely mandatory because these buildings, with their dense equipment and massive concrete slabs, they are just tremendously heavy.
And all of that planning, securing the land, locking in utility slots, that requires serious, immediate cash. Which brings us to 1C, capital structuring and funding.
Right. You have to align the financial, close securing all the debt and equity with your long-lead equipment orders, and the final investment decision, or FID, triggers.
So the money has to be ready to go.
Capital readiness must be treated as a construction precondition. It's not something you sort out while the foundation is being poured. If funding delays occur, they directly disrupt procurement lead times for that critical equipment.
The transformers, the generators.
The custom-made gear that takes a year to fabricate. Delaying a multi-million-dollar transformer order because the final loan paperwork wasn't signed is a rookie mistake that can cost tens of millions in rescheduled supplier fees and project delays.
So the finance team is just as critical as the engineering team in these early stages.
They're inseparable.
Okay, that moves us on to phases 2 and 3, which cover design, compliance, and procurement. Stage 4, the concept design brief. Sounds like the core specification document, the Bible that everyone on the project references.
It is. It's the foundational contract for the entire physical structure. This is where you establish the fixed scope baseline. You detail the gross floor area, the white space for the racks, the support zones, the precise cooling strategy, and critically, the redundancy requirements.
Redundancy, that's the fault tolerance standards, right? We hear the industry language all the time. N plus 1, 2N.
Exactly. You have to specify if it's N plus 1, or 2N redundancy, and align that with recognized certifications like the Uptime Institute's tier standards.
So what's the difference?
N means you have exactly the components you need, with zero backup. It's very rarely used for anything critical. N plus 1 means you have one redundant component for every necessary component. If one UPS fails, there's one spare to pick up the load.
And 2N.
2N means you have two fully independent systems, often called the A side and the B side. Each one is capable of powering the entire IT load by itself. The design brief locks in that level of reliability, and that in turn dictates the budget and the physical footprint of the building.
Okay, and then stage 5 is ESG and sustainability integration. This has just soared from being a footnote to a mandatory headline requirement in modern data center development.
It's completely foundational now. It's primarily driven by investor and regulatory pressure. Operators have to set targets for PUE power usage effectiveness EUI, which is energy use intensity and carbon intensity. And they have to align with global frameworks like GRESB or LEED.
And our sources highlight a crucial project management tip here. ESG specs must be written into the procurement documents right up front, from the moment you start specing out your chillers and generators. Why is that so vital?
Because if you wait until the design is finalized and the equipment is ordered, and then you realize those components don't meet your carbon intensity targets or your efficiency scores, for instance, maybe the generators have an unexpectedly high non-NOx emission profile non-compliance, will force costly redesigns and huge delays later in the process.
So it's not just about optics.
It's about finance. Integrating sustainability is fundamental. GRESB scores directly influence a project's cost of capital and its eligibility for major green investment funds. It's a fundamental financial compliance step now.
All right, stage 6. This feels like the bureaucratic hurdle, the time sink, permits and entitlements. The complexity of securing approvals from everyone, from the local planning board to environmental agencies.
That's a huge one. It involves securing zoning variances, fire department sign-offs, those utility interconnection permits, and environmental approvals, especially related to things like water usage for cooling.
And the key point is?
The key point is that permits often gate mobilization. They are critical path items that you just cannot accelerate by spending more money. You cannot put a shovel in the ground until the city, the fire department, the utility commission, and often state environmental regulators have all signed off on your detailed plans.
So a project manager has to live and breathe that permit status.
They have to embed it into their critical path schedule, because grid approvals and zoning conditions frequently stall the start of the build, even after all the money is secured.
Then comes the moment of truth in stage 7, long-lead equipment procurement. This is where the global supply chain collides head-on with the construction schedule. These items define the entire delivery window.
This is where it gets really interesting and, frankly, terrifying for the project manager. You're identifying and specing the massive custom critical systems, the high-voltage transformers, the complex switchgear that manages those AB power paths, the diesel generators, and the massive chillers.
And these aren't off-the-shelf parts.
Not even close. These items often have global supply chain lead times measured in 6 to 18 months. The PM tip from our sources is blunt. Missing a vendor slot for one of these items can push your go live by quarters, because you can't just go and buy a 100 megawatt utility grade transformer at the local hardware store.
So if a major hyperscale client signs a letter of intent, an LOI, to occupy the facility in, say, Q4 is 2026, that commitment has to align perfectly with the date you secure the manufacturing slot for your custom power gear that might take 16 months to be built in Asia.
Precisely. You have to coordinate the design freeze with the procurement timing to avoid these mismatched timelines. You don't want the design team changing a specification like, say, reducing the footprint of the generator pad just as that component is about to start production in a factory overseas.
It's a digital synchronization across continents.
And hundreds of suppliers. It's an immense logistical challenge.
And that detailed, risky balancing act leads us to stage 8. The end of the development phase. The final investment decision, or FID, is the official go-no-go gate.
FID confirms the project is fully scoped, fully funded, and legally cleared to build. This is the decisive moment. The design is officially frozen, final specifications are locked for the general contractors, capital drawdown is confirmed with the lenders, tenant LOIs are formally activated, and procurement staging is matched to the construction sequences.
And the ultimate key insight here.
Repeated across all reliable sources is this: never, ever initiate site work or issue build contracts until all FID criteria are complete and approved. Proceeding prematurely guarantees risk, delays, and massive cost overruns. It's the moment of ultimate commitment.
Wow, that entire pre-construction phase is just an incredibly complex dance. You're balancing utilities, finance, global supply chains, and local zoning boards. It sounds less like construction planning and more like international strategic logistics.
It is. And only once that financial and legal fortress is built can we finally start talking about the structure itself.
All right, let's move to section 2 then, the architecture. Because once those plans are locked, the physical structure has to withstand these immense internal loads and external threats, all while maintaining a perfect internal climate for that sensitive IT gear.
The structural strength challenge is completely unique. Unlike, say, a standard office tower, where the floor load is designed for people and desks, maybe 500 kilograms per square meter.
Right.
A data center floor is holding up sensitive, incredibly heavy IT equipment that runs 247/365. This structure has to be an absolute bunker.
How heavy are we really talking? Can you give us a visual analogy that would stick with someone?
Okay, so the floors have to be heavily reinforced to handle extremely high server rack loads. We're talking specifically 1,500 to 2,000 kilograms per square meter.
Which is a lot.
To visualize that concentrated static load, imagine taking 2 full-grown prime-weight dairy cows and placing them on every single square meter of the IT floor space permanently for decades.
Wait, two cows per square meter.
2 cows on every single square meter. That is the kind of continuous, non-negotiable stress the structure has to endure without failing.
I am never looking at a server rack the same way again.
Yeah.
That puts the engineering demands into a whole new perspective. It's not just a big empty room, it's a high-density, multi-ton foundation designed to withstand perpetual stress.
And that structure also has to provide serious durability and resilience against external forces. This includes strict adherence to seismic load resistance codes, which is necessary in fault zones, and wind load compliance for facilities exposed to high winds or hurricane risk.
And it's not just the big things, right?
Critically, no. There has to be stringent vibration control. Vibrations, even slight ones from the building's own HVAC systems or from nearby road traffic, can interfere with the operation of sensitive hard drives and networking technology. They can cause read-write errors or even premature component failures.
So what do they do about that?
They often incorporate special isolation pads under the slab and use extremely rigid structural designs just to mitigate that internal operational vibration.
I see our sources mention BIM a lot, building information modeling. I assume coordinating these massive structural elements with all the necessary power and cooling systems is just impossible without advanced digital tools like that.
It's absolutely crucial. BIM allows the structural, the mechanical, electrical, and plumbing teams, the MEP teams, to collaborate in a shared digital space. When you have miles of cable trays, massive chilled water pipes, and huge air handlers that all need to occupy the same ceiling space, BIM lets the engineers coordinate every layout down to the millimeter.
So it's about avoiding clashes on site.
Exactly. This digital process is essential for streamlining workflows and, most importantly, avoiding those costly construction clashes where, a huge pipe runs right through where a critical support beam or an electrical switchgear panel was planned. That coordination saves months of rework on site.
We touched on strategic site selection earlier, but from this new structural and operational perspective, it feels like it's worth revisiting. What makes a site perfect for the long term?
When you look at the structure and its environment together, you have to ensure that long-term operational efficiency and resilience. This means mitigating environmental risks, being outside of floodplains, avoiding active seismic zones if at all possible. It also means ensuring the building materials themselves can handle the external environment, like high humidity or extreme temperature swings, while still providing that optimal connectivity for secure cloud delivery with minimal latency.
Proximity to major fiber routes is non-negotiable.
Absolutely non-negotiable.
Okay, now we have to move to the internal climate management. This is the biggest financial and environmental challenge of these facilities. The cooling systems and thermal management. This is the energy monster we talked about earlier. High-performance servers generate intense heat, and with AI, that intensity has just gone parabolic.
Cooling can be the single largest contributor to a data center's energy bill. It often accounts for 30 to 50% of all the non-IT power use. So an intelligent adaptive cooling system is essential to manage operating costs and your carbon footprint, not just to maintain uptime.
And the higher the power density.
The higher the power density, as you move from 10 kilowatts per rack to 50, 80, or even 100 kilowatts per rack for AI workloads, the more intense the heat output, and the more traditional air cooling strategies just start to fail.
So what are the popular energy-efficient strategies that are used today to fight all that heat?
The foundational methods are cold and hot aisle containment systems. You physically separate the cold intake air, which the servers use, from the hot exhaust air that the servers expel. You just prevent them from mixing, and that maximizes your cooling efficiency.
But for modern high-density AI clusters,
For those, we are moving very fast toward liquid cooling,
why is liquid cooling becoming so essential for AI specifically?
because air simply cannot remove heat fast enough at those extreme densities. Liquid cooling, whether it's through cold plates attached directly to the heat-producing components like CPUs and GPUs, or full immersion cooling, where the servers are literally submerged in a non-conductive fluid, it's just exponentially more efficient at heat transfer.
So it's becoming a requirement, not an option.
It's becoming a design requirement for any new facility that's focused on hosting advanced machine learning and AI processing.
And for facilities in certain geographies, you can leverage the environment itself, right?
Exactly. You leverage the environment to reduce your mechanical cooling needs. Free air cooling works incredibly well in cold, dry climates, like in the Nordic countries, by drawing in and filtering outside air directly.
And in warmer places.
In warmer climates, you might use evaporative or adiabatic cooling solutions. These use water evaporation to reduce the air temperature. They offer a good balance of cooling capacity and energy efficiency, though they do require significant water resources, which becomes its own complex planning issue you have to solve.
How do engineers figure out the best arrangement? I mean, they don't just build it and then test the airflow, do they?
No, absolutely not. The engineering optimization is critical, and it happens entirely in the virtual space first. They use CFD simulations, that's computational fluid dynamics.
Okay, what is that?
Think of CFD as running sophisticated virtual heat and airflow tests inside a perfect digital twin of the data center. Engineers can explore the most effective airflow, fan placement, and layout configurations. They can digitally simulate a heat wave inside the building to ensure that their cold aisle containment doesn't suddenly fail when the racks hit their peak load.
So it's about reliability and efficiency.
It ensures thermal reliability and, crucially, it minimizes overcooling, which saves massive amounts of energy over the facility's decades-long lifespan.
That detailed transition from virtual planning and risk management to this massive physical construction is just stunning. Let's move to Section 3, the lifeline. Because none of this works without perfect uninterrupted power. Reliability is absolutely everything.
Indeed. The electrical infrastructure is the heart and soul of the data center. It must be meticulously engineered, often requiring those 20 to over 100 megawatts for the hyperscale facilities. This power is the absolute backbone. It guarantees uninterrupted functionality for all the critical components: the servers, the cooling, the storage, the networking.
And if that power falters for even a millisecond,
The financial consequences are immediate and they are severe.
how do they design for power then, given that demand is only going up, especially with AI consuming these vast amounts of energy?
Adaptability and scalability are the key design principles. The electrical infrastructure has to incorporate modular approaches. This means designing the core utility feed and the primary switchgear so that additional modular power blocks, say a new 10-megawatt section, can be added seamlessly without disrupting ongoing operations.
So you're building in room to grow.
If you project a 15 to 20% demand increase over the next decade, your power system needs to be able to accommodate that growth smoothly, often by incorporating empty slots for future components right from day one.
Let's talk about the key components in that power chain. Let's start from where the utility feeds in and follow it right to the server.
Okay, so electricity enters the data center at a high medium voltage level, typically from 13.2 kilovolts up to 27.6 kilovolts. The transformers are the first critical component. They regulate and convert these high voltage levels down for the internal networks.
And then?
Next, you have the PDUs, or power distribution units. These take the facility power and they disseminate it throughout the white space, ensuring the load is balanced and that those redundant paths are available.
And what happens the millisecond the utility grid hiccups or, completely fails?
That's where the first line of defense comes in. That's the UPS, the uninterruptible power supply systems. These are massive arrays of batteries that provide instant backup, usually for about 15 to 30 minutes during short outages or just while the main backup systems are initializing.
So the servers never even know the grid went down.
They never detect a break in power. Now, if the outage is prolonged, the backup generators activate. And it's critical that these generators have ratings close to their prime rating so they can handle the full power load during an extended utility service disruption. Fuel management for these generators is a massive logistical challenge in itself.
And then bringing that highly protected, conditioned power right to the server rack. How does that work?
That's the job of RPPs, or remote power panels, and flexible cabling solutions called power whips. They are intermediary devices that enhance power delivery closer to the IT gear. They allow for flexible configuration of power delivery to different racks with different demands, and importantly, they reduce voltage drops over long cable runs, which can compromise reliability.
So the chain is utility power into transformers, regulated by switchgear, distributed by PDUs, instantly protected by a UPS, backed up by generators, and finally delivered by RPPs and whips. It's just this complex, multi-layered system designed solely for one goal: 100% uptime.
And every single layer is designed with redundancy, which brings us to our next point: eliminating single points of failure.
Right, we mentioned N+1 and 2N earlier. Let's delve into the practical and financial trade-offs between those industry standards.
These standards define the level of fault tolerance, and they directly impact the facility's capital expenditure. N+1 means having what you need, which is N plus one extra component, the +1. It's cheaper to build, it's cheaper to run, but it can only handle one failure at a time. If two failures occur in quick succession, the facility goes down.
And 2N, that seems to be the gold standard for hyperscale.
2N, or sometimes 2N+1, means you have two entirely independent parallel systems. We often refer to them as the A side and the B side. Each system is fully capable of carrying the entire IT load by itself.
The whole thing.
The entire load. If system A fails completely, let's say there's a switchgear fire system, B can take over instantly without any interruption whatsoever. This dual-path reliability means separate transformers, separate UPS systems, separate generators, separate distribution paths, and even often separate pathways cut right into the physical concrete structure.
That dual-path setup sounds absolutely necessary for high-stakes operations, but doesn't running a completely redundant 2N system essentially double your capital expenditure up front and increase your operational cooling costs? How do companies justify that financial hit?
That is the core question, and it's always a risk assessment. Companies justify the 2N expense because the cost of downtime is exponential. For a major cloud provider, a single hour of downtime can lead to tens of millions of dollars in lost revenue, contract penalties, and, reputational damage that's hard to quantify.
So the extra cost is just insurance.
The incremental cost of that second, fully independent system is simply insurance against a catastrophic loss. You reserve 2N for your mission-critical IT infrastructure, while sometimes N+1 is sufficient for supporting elements, like administrative offices or specific low-priority storage racks.
We're also seeing emerging solutions to complement this, like the rising popularity of BES battery energy storage systems. How do these fit into the traditional UPS and generator scheme?
BESS is rapidly gaining traction, particularly for supporting renewable integration. These systems store surplus renewable energy from solar or wind farms and provide a reliable, long-duration power supply during low production periods. They act as a bridge between that instantaneous UPS support and the longer-term diesel generator activation.
So they smooth things out.
They often clean up grid fluctuations and make the overall system more resilient and more environmentally compliant.
Okay, moving on, let's talk about distribution and efficiency, starting with the difference between single-phase and three-phase power in this context.
For large data centers, three-phase power is the absolute standard, often generating 415 volts internally. Single-phase power is what runs your household appliances. It's simple, but it's very inefficient for large-scale operations.
Why is that?
Three-phase delivers constant, smooth power. It offers higher efficiency, greater capacity, and it reduces the necessary wiring size and cost compared to trying to distribute that same massive load via single-phase circuits.
The efficiency also hinges on the physical wiring itself, I have to imagine.
Absolutely. Cable integrity is crucial. The sheer volume of copper and the quality required is just staggering. The cables have to be resilient, robust, and high caliber to prevent energy wastage, which is known as I squared R losses,
Yeah.
and maintain consistent functionality over decades.
In organization matters.
Organized cabling structuring, often managed through overhead basket trays, is vital because it mitigates the threat of electrical disruptions, it bolsters efficiency, and it supports easy maintenance access down the line.
And the ultimate universal metric for measuring all of this efficiency work is PUE.
Right. PUE, or power usage effectiveness, is the global industry standard for energy efficiency. It's calculated by taking the ratio of the total energy consumption of the facility. That's everything, including cooling, lighting, security, to the energy used by the servers themselves.
So a PUE of 1.0 would be perfect.
Mathematically perfect, yes. It would mean every single watt of power goes directly to the IT gear.
So if the current industry average PUE score is about 1.58, what is that extra 0.58 being spent on?
That's the overhead. It's the cost of maintaining the environment around the servers. That 0.58 goes to power the cooling systems, the UPS losses, the transformers, and all the lighting and administrative components. When you consider that the servers alone account for 50 to 70% of the total energy consumption, lowering that PUE score, getting it closer to 1.2 or 1.1 means billions of dollars in lifetime energy saving.
It's the highest target for innovation.
Absolutely. Because efficiency directly equals profit and sustainability.
That's a huge target. Which leads us into our final section here. Sustainability and future-proofing. How are data centers reducing their footprint and evolving into these green data centers?
Well, it starts with sourcing and commitment. They are drastically reducing their dependence on fossil fuels via wind, solar, and especially long-term green power purchase agreements, or PPAs.
What are those exactly?
They're contracts where the data center agrees to buy the renewable energy output from a specific facility, like a new solar farm. Major firms are setting precedents by pledging to operate their data centers entirely on renewable energy, often demanding these projects be built locally to them.
And the circular economy aspect.
Yeah.
This always fascinates me, this idea of turning waste heat into a resource.
That's the beauty of heat recovery systems. Instead of just dumping all that waste heat into the atmosphere through cooling towers, that captured energy, often in the form of warm water or air, can be redirected to municipal heating networks, nearby office buildings, or even agricultural greenhouses.
So the data center heats the town.
We are seeing major projects in Northern Europe where the data center literally heats the surrounding community. It contributes positively to the local economy and massively cuts its environmental impact. It's a win-win.
And what about in terms of the construction materials? I mean, these are massive buildings, so the materials have to matter.
They do. We're seeing the use of low-carbon materials like recycled steel or eco-concrete mixtures that use industrial byproducts. Water management is also critical. Implementing water-saving systems like closed-loop cooling or capturing and treating rainwater addresses the massive water consumption these facilities have historically required, especially those using evaporative cooling.
Finally, how do they future-proof for that projected 15 to 20% demand increase in compute power we talked about? How do you build flexibility into something that seems so rigid?
Through disciplined modularity. Modular power systems and prefabricated IT blocks allow the systems to be scaled up as needed without disrupting any ongoing activities. They often plan for shell space, just empty sections of the building, and they can install new modular power skids when required.
So you're building in the ability to adapt.
It's about building flexibility into the electrical and mechanical design so they can adjust seamlessly to escalating demands over the next 10 to 20 years without needing a full shutdown or a multi-year renovation.
That adaptability is crucial. And there is one advanced concept that keeps popping up when we talk about efficiency: DC power distribution. We currently use AC. Why is there so much interest in direct current?
It's gaining interest because it addresses the Achilles heel of efficiency. IT gear, at its core, runs on DC power. The traditional design converts the utility's AC power to DC inside the UPS, then back to AC for distribution, and then finally back to DC again inside the server's own power supply.
That sounds inefficient.
Every conversion step loses energy as heat. By moving toward a facility-wide DC power distribution system, you could reduce those AC to DC conversion losses significantly. It would simplify the infrastructure and offer improved overall energy efficiency and reliability, though it does require a significant departure from current utility standards.
Fascinating. So we've taken this incredibly complex journey, from securing the land and the multi-year utility slot through calculating those concentrated cow-level structural loads to installing 2N redundant power paths and cutting-edge CFD-optimized cooling systems.
We have, and I think we've established that the modern data center is not just a building. It's an intricate, integrated machine. It's defined by its resilience through meticulous redundancy planning and its relentless pursuit of efficiency, which is tracked by that vital PUE metric.
And the complexity of the coordination is just staggering. You have structural planning, MEP teams, IT teams, financial managers, utility access. All of it has to align perfectly under these strict financial and ESG compliance gates. It really sounds like the real risk mitigation happens long before construction even begins. You're essentially building a financial and legal fortress around the project.
Exactly. Every stage is interdependent. The decisions you make in the planning phase about power density directly dictate the materials used in the structure, the capacity of the chillers, and the ultimate operational efficiency of the building for the next 30 years. It requires a level of synchronous planning that is truly unparalleled in the construction world.
So we've seen how meticulously engineers plan for the future, accommodating this massive compounding growth in AI and compute loads. If current design strategies rely so heavily on redundancy, things like 2N power paths and diesel generators to guarantee uptime, what unforeseen technological shift might finally break this reliance?
That's the billion-dollar question.
What kind of quantum leap in server efficiency, perhaps, or widespread adoption of DC power might push the entire design paradigm toward true net-zero resilience? And finally, make the massive climate-controlled diesel generators obsolete? Something for you to consider next time you hit send.
A provocative thought indeed. The race is on to answer that question, and the future of sustainable computing really hinges on finding that solution.
That was the deep dive. We hope you feel thoroughly informed on the invisible infrastructure powering our digital lives.
Thank you for joining us.